Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 4, Section 1, Chapter 7, Topic 2. Categorizing Semiconductor Package Fatigue Examples. Introduction. Fatigue failure is a significant concern in semiconductor packaging, where repeated cyclic loading can lead to cracks, delamination, and ultimately device failure. Understanding the various types of fatigue failures and their underlying mechanisms is essential for designing reliable and durable semiconductor packages. This overview categorizes semiconductor package fatigue examples based on their characteristics, causes, and manifestations, providing insights into the diverse challenges associated with fatigue in semiconductor packaging. 1. Thermal fatigue. Thermal fatigue occurs when semiconductor packages are subjected to cyclic thermal loading, such as temperature cycling during device operation or thermal shock events. 1. Examples of thermal fatigue in semiconductor packaging include: 1. Dielectric cracking. Differential thermal expansion between materials, such as dielectric layers, substrates, and encapsulants, can induce thermal stresses, leading to cracking and delamination of dielectric layers. 2. Solder joint fatigue. Cyclic temperature changes cause thermal expansion and contraction of solder joints, leading to fatigue damage, crack initiation, and eventual failure of interconnects, such as ball grid arrays, BGAs, flip chip packages, and surface mount devices, SMDs. 3. Wire bond fatigue. Thermal cycling can induce fatigue damage in wire bonds, where the repeated expansion and contraction of the bonding wires lead to wire deformation, bond lifting, or bond breakage, compromising electrical connectivity and package reliability. 1. Mechanical fatigue. Mechanical fatigue results from cyclic mechanical loading, such as mechanical shock, vibration, bending, or flexing, experienced by semiconductor packages during handling, transportation, or device operation. 1. Examples of mechanical fatigue in semiconductor packaging include: 1. Lead frame cracking. Mechanical shock or vibration can induce fatigue cracks in lead frames, particularly in thin and narrow sections, leading to lead frame cracking, package warpage, and device malfunction. 2. Substrate fatigue. Flexing or bending of substrates, such as organic substrates, FR4, ceramic substrates, aluminium oxide, or flex substrates, polyimide, can cause substrate fatigue, resulting in delamination, crack propagation, or solder joint failure. 3. Package warpage. Cyclic mechanical loading can induce package warpage, where the semiconductor package undergoes dimensional changes or deformations, leading to stress concentrations, crack initiation, and reduced reliability. 1. Environmental fatigue. Environmental factors, such as moisture ingress, chemical exposure, and corrosive agents, can accelerate material degradation and fatigue failure in semiconductor packages. 1. Examples of environmental fatigue in semiconductor packaging include: 1. Moisture-induced delamination. Moisture ingress into semiconductor packages can lead to delamination of dielectric layers, substrate layers, or encapsulant materials, compromising package integrity and reliability. 2. Corrosion-induced cracking. Exposure to corrosive environments, such as high humidity, acidic or alkaline solutions, or corrosive gases, can promote material corrosion, crack initiation, and structural degradation in semiconductor packages. 3. Chemical compatibility issues. Incompatible materials or chemical interactions between package components, such as adhesives, coatings, or sealants, can lead to chemical degradation, embrittlement, or fatigue failure in semiconductor packages. 1. Electromigration-induced fatigue. Electromigration is a phenomenon where the migration of metal atoms in conductive lines or interconnects leads to material voiding, Hillock formation, and eventual failure. 1. Examples of electromigration-induced fatigue in semiconductor packaging include: 1. Void formation. Electromigration-induced void formation occurs when metal atoms migrate away from high current density regions, leading to void nucleation, void growth, and eventual open circuit failure in interconnects. 2. Hillock growth. Electromigration-induced Hillock growth occurs when metal atoms migrate towards high current density regions, forming protrusions or hillocks on interconnect surfaces, which can lead to short circuit failure or mechanical stress concentrations. Thanks for watching. Please like, share, and subscribe.